Hello, here's some notes on using the TI-84 with continuous probability distributions. Now, I've covered this in some other videos and some other notes, but I thought this is a nice little 3-page summary that basically goes over everything that you need to know about using the calculator with distributions in general. And there are basically two parts. Part one is where we are given the PDF formula, and part two is where we're given the CDF formula. So we're either given a command or a formula for these things, and we can see what we can do with the PDF and what we can do with the CDF, and how to do this on a TI-84 calculator. Okay, so let's just dive in. The directions are basically on the left, and on the right there's an example worked out. So part one is going to consider that a formula for the PDF is given. So I've given an example here. For this particular one, PDF of x is 3/16 times the square root of x minus 3. And this is going to be valid. X is going from 3 to 7. And it's 0 otherwise. So the 0 otherwise means we can basically ignore everything outside of that. So the first thing we're going to do is enter a formula for y1. So I just press y equals, and then type this in as you see here on the screen. Okay, this is the newer operating system on this particular screen. The older one looks very, very similar to this. Then you need to choose an appropriate window and graph it. Now sometimes it can take a little bit of trial and error to find appropriate window limits. Okay, and I chose the same limits that I usually use for CDFs here of -0.2 to 1 for y. And the x's are actually chosen for us here. We know that this is defined from 3 to 7, 0 otherwise. We can ignore everything to the left of 3 or to the right of 7 in this case. So it's pretty clear that we want a graph between 3 and 7. Now, if this is not a good window vertically, then we might change it. But we know that the 3 to 7 is the correct thing. And so we can graph that, and you'll see that in this picture right here. And so, now, the next thing is this really a legitimate PDF? How do we tell? Well, what characteristics should a PDF have? Well, the graph should always have y values that are either positive or 0, but never negative, over the appropriate interval. So from 3 to 7, which is what we have graphed here, we can see that this graph never goes below the y-axis. And so that's below the x-axis, excuse me. So never a y is 0. And so that's exactly what we need to find. And then that's number one. And number two, the total area between the PDF and the x-axis. Okay, so between this curve and the x-axis right in here, that total area has to be 1. Now there's no area between the curve and the x-axis to the right of this or to the left of this window. So it's only between these particular x values that this thing even exists in this example. Now how can we find that area? Well, there's two ways we can do it. We can do it at the home screen, okay, and the home screen we type in, well, if we've got the old operating system, we type in function integrate, we just type in y1, comma x, comma a, comma b, and a and b are our limits, so in this case that's 3 and 7, and of course we're assuming our formula is in y1, and then function integrate is math 9. So you want to hit math 9 and pull this up, and if you got the older operating systems, this will look like function integrate. To get y1, you have to put variables, VARS, then right arrow to function, and then or y variables, then choose function, and then it'll be y1, y2, or whatever will be there. So then you choose y1 from that list like that. This will always be x for the second part. A and B are our interval, so which includes all of it basically. So anything beyond this is 0. So in this case it would be 3 to 7. Or if you got the newer operating system, it'll look like this. You can actually see it here, 3 to 7 of y1, and it's always an x for this last thing after the dx. Basically you can think of that as just identifying what our variable is, which will always be x for us. And we do this, it should turn out to be 1. You might notice that this particular one, it's not exactly 1, it's very, very close to 1. Sometimes you can adjust that if these limits are not particularly right, but sometimes this is using approximation techniques, so sometimes it could be off just a little bit in the last 2 or 3 digits here, but for most of the digits it will round off exactly to 1. Okay? Now, sometimes these things go on to infinity or to minus infinity. Sometimes they go from 0 to infinity. Sometimes they go from negative infinity to infinity. We can't, unfortunately, put in infinity or minus infinity for A or B there. Okay, what we can do is put in something that's way out to the left for A and way out to the right for B, so far out there that anything beyond that is practically 0 for an area. We can also see the area and graph it, shade it, and calculate it by doing, at the graphing screen, press Calc, which is second trace, and select number 7, which is this integral, that sum of the probability density, and again enter those same values of A and B for the lower and upper limits, and then it'll shade the whole thing, and it should return a value of 1. Again, it's approximately 1 here. Now, when you finish shading any time, be sure you always press Draw, which is second program, and then select 1, which is Clear Draw, and hit Enter, and that will erase the shading after you've seen it. So the next time we go in and shade something, it will shade correctly. Like this one, I turned in and shaded this next part. If I hadn't erased it, it wouldn't have shaded correctly. You would have seen everything shaded, so that's not good. So be sure you clean up the shading after you finish each time. Now, we can also, so we've verified that it's a legitimate PDF. Now what we can do is, so we know it's a legitimate PDF. What we also know we can do is to find probabilities. Now, probabilities on a PDF graph are areas between the graph of the PDF and the x-axis over whatever interval we're interested in. So, for example, in this example, I want to find the probability that x is between 4 and 6.2, and I can do that with the shading. Okay, if I'm at the graphing screen, I can again push second trace to get Calc, and then select number 7. That number 7 is basically our area shader, area calculator. Okay, and so just press that number 7 to get our area, and then enter in your left endpoint. It'll say lower limit, push 4, enter. Then it'll say upper limit, press 6.2, enter, and then it will shade this. This left edge right here is 4, x of 4, and this right edge is an x of 6.2. It shades everything in between those two that's below the curve and above the x-axis, and that's the region we're finding the area of, and that area turns out to be about 0.5905 whatever, and that is also the same thing as the probability there. Okay, so the probability that 4 is less than x, which is less than 6.2, is about 59%, about 0.59. Okay, and it doesn't matter on a continuous distribution whether you have or equal to's here or not. So if you said 4 is less than or equal to x, which is less than or equal to 6.2, it'd been exactly the same thing, because the probability that x actually equals 4 is actually 0 in a continuous distribution. Okay, and we can do this from the home screen, as you can see in this last one here, by doing pressing Math 9, and it gets this thing, and we have blanks here where the 4 is, so you fill in the lower limit there, 4. There's a blank where the upper limit is, you put in the upper one, which in this case was 6.2. There's a blank here in the parentheses, and you put in you can either type in the formula, but you don't want to have to keep typing the formula. That's one of the reasons why we put it in Y1. So you can just say Y1 here, and then it's always x for this last blank over here after the D. Or if you've got the older operating system, this would be written as function integrate FNINT. Again, it's just Math 9 is going to either get you, it's going to look like the FNINT, or it's going to look like this with the stylized S there and so forth. And that'll open the parentheses for you. You put in your function first. It's still the same 4 things. You still got to put in Y1. You still got to put in the X. You put in the 4 and the 6.2. It's just you don't put them in where they go in this version. You put them in this order here. The Y1 first, then the X, then the lower bound, the 4, and then the 6.2. So it looked like FNINT of Y1, comma, X, comma, 4, comma, 6.2. And then the output would be the same. We can also use the PDF to compute the mean and variance and standard deviation of the distribution. Remember that the mean, mu, is the expected value of x. Okay? And when you do the expected value of something, you multiply that something by the probability, the PDF, and then you sum it up. Well, summing it up in the continuous case is this. That's what this funny looking S here is doing. It's summing them up, just like the funny looking sigma was our S for summing them up in the discrete case. So we're just summing up our x's times our probabilities, same as we did in the discrete case, but now we're just doing it in, this is sort of the continuous version of that. Okay, we're going to need our calculator to do this most likely, unless you know some things that we're not covering in this class. You're going to need a calculator to do this. Okay, and so we just pull this up like this. Again, you use Math 9. It will either look like FNINT of, and then x times PDF of x, and so forth. You can see that here in the second screen on the right, and that is that's the old version of it. Function integrate x times y1 comma x comma, in this case 3 to 7, because 3 to 7 was everything we had. It's got to cover everything. It's got to cover all the possibilities for x. And I stored that as m because that's the mean. In fact, I think this one's actually rounded off a little bit. I think the mean is exactly 5.4 in this case, but it's going to be accurate to many decimal places. If you do it in the new operating system, it looks like this one at the top screen, where it goes from 3 to 7 again, and it's just x times y1, and then dx is always on the outside. And again, I stored it as m. Now, one of the reasons why I might want to store it as m is I'm going to use m, or mu, in the computation of the variance. And the variance is written as sigma square, and if you remember from our discrete distributions, what we did is we took x's, subtracted the mean, then squared them all, then multiply them by the probabilities and add them up. Well, that's what we do here. Again, it's the expected value of x minus mu square. So we take x minus mu square, multiply it by the PDF, and then sum it up. Again, this sum is this is called an integral sign. It's this funky looking little s here, long skinny s, for summing up this particular thing. Okay, and so we need to do this. And so here it is in the old operating system. Notice I've got mu stored as m, so it's just Math 9 will give you function integrate. It'll open parentheses for you, then you open another one, put in x minus m, close parentheses, then square it, times y1, comma x, comma, well, in this case 3 and 7, because 3 and 7 include everything that matters. Everything outside of 3 and 7 is 0. And so work that out, and that is the variance, and of course just take the square root of that answer to give you the standard deviation. The next screen is what this exact same thing looks like if you do it with the newer operating system and do the math print turned on. Now, so notice that we can find probabilities directly from the PDF. We can find the mean, we can find the variance, the standard deviation by using that without knowing the CDF. But if we want to do inverse probabilities, we need to get our hands on the CDF. So, inverse probabilities would include the median. So to find the median, we're going to need to find, or percentiles, inverse probabilities like that, we need to find the CDF. And luckily there is a way to approximate the CDF with the calculator. So again, assuming y1 is the PDF, then we let y2 be function integrate y1, comma x, comma a, comma x. Okay, so the last one's always x, the second one's always x, the first one is wherever you have the PDF, and the third one there, the a, is a value to where there's nothing to the left of a. Okay, so nothing to the left of a, you can just use a. I think in one of the earlier videos I may have shown you a slightly different way to do this. This is actually a better way. Just do it this way. Find a value a so there's nothing to the left. Now, what if there is no such a? What if it goes to negative infinity? Well, then just go far enough out. There should be some value out there so far to the left that everything beyond that is so small that we can just ignore it, and then use that value as your a. Well, in this case, it's only defined from 3 to 7, so A is going to be 3. But now the X part there at the end is going to be a variable. And again, you can see that written as a... so here it is on the left one down here, on the far left here. This is how it would look if you have the new operating system, and then this one here in the second screen is how it would look if you have the old operating system. But either way, it's the same thing. Also, I put my cursor on this and hit enter once to make this a thicker line, or a thicker mark. So the curve is going to be thicker for the CDF. That's optional. You don't have to do that. But then graph it. Now, be patient, because the calculator is doing probably thousands of calculations to do this approximation. So it's a really kind of a slow process. It'll take several seconds for this to work out, maybe even a minute for it to work this out. But it will eventually graph this. How do you know it's an appropriate CDF? Well, it should start at 0 and end at 1 over that appropriate interval. Okay? When we're doing further calculations with this CDF, since this CDF is approximated, again, it may take a little bit longer for those calculations to happen, particularly to do the graphs. So, let's see, above we've already figured out the mean and the standard deviation and the variance. If we want to use the calculated CDF, the approximated CDF, to find the median, then the median, remember, is it's the point where half of the data is below it. The cumulative probability is a half. Well, the y values on the CDF are exactly the cumulative probabilities. So if we let y3 here be 0.5, graph that across, where those two cross each other is going to be the x value of that's going to be the median. The y value is of course going to be 0.5. And so we see the median is about 5.52. To find the median or percentiles or inverse probabilities, we have to either compute somehow the formula for the CDF, or they have to give it to us, or we can use this technique here to get the CDF approximated if we are just given the formula for the PDF. Okay, now let's go the other way around. Suppose we're given a formula for a CDF. New example. This time the CDF is given 1 over 1 plus 20 times e to the negative 0.05x. This is actually defined for all x. Okay, so this one actually goes from negative infinity to infinity. So we choose an appropriate window and graph it. Well, we need to go negative infinity to infinity, but we can't really do that, so we're going to go out far enough to where we can see it level off. Now, a CDF, how do we know it's a legitimate CDF? Okay, it should be one continuous connected piece. It should start at 0 and end at 1, and it should never decrease in between. So it should be climbing the whole time. It might level off for a while, but it never goes back down. Okay? And so you should see it level off to 0 on the left and 1 on the right. So you kind of have to adjust your window till you see that. For the vertical part of your window, it's pretty easy. You can always use negative 0.2 for Ymin and 1 for Ymax. Really, you could use 0 for Ymin and 1 for Ymax and get the whole graph, because it's never going to go below the x-axis. Never going to go below y equals 0. However, I go a little bit into the negatives because I like a little dead space at the bottom of the screen, because later on I may do things like tracing and calc intersect and, maybe compute an area or something. Wouldn't be an area on this one, but it might be for a PDF. So I would those values come out down here at the bottom of the screen, so I don't really want those to cover up my graph, so I kind of move my graph up a little bit by leaving me a little bit of space down there. But there shouldn't be anything graphed down here in this bottom part, below the x-axis. Okay, and so a little trial and error. On this one, I went from negative 100 to 300, marked it off in 50s on the x-axis. And then I used my standard negative 0.2 to 1 on the y's and marked it off in 0.1s. And so now we see it coming in at approximately 0 on the left, coming up, and then leveling out at 1 on the right. Now in this particular one, it actually has an asymptote of 1 on the right and an asymptote of 0 on the left. So graph never actually hits 0 or 1, but it approaches those values as you go way out to the left or right. Okay, and that can happen if we have one of these that goes on to infinity. Okay, so that looks like a legitimate CDF. Looks good. Okay, now we can use the CDF to compute probabilities. Now remember, on the PDF, probabilities are areas. On the CDF, probabilities are y-values, specifically cumulative probabilities are y-values. So the y-values on the CDF are always, on the PDF, they'd be shaded from that value to the left. They're always left-tailed areas, are the y-values on the CDF. So, for example, if we want to find the probability that x is less than some numbers, say b, then we just need the y-value of b. We need CDF of b. Okay, and there's several ways we can do that. We can get it from a table. We can also get it from a trace if we've got the graph up there. So one easy way to do it is just hit trace and enter the value b, and it'll return the probability. If you're at the home screen, you can just do y1 of b, and that will return it. Again, I'm assuming y1 has the formula for the CDF. Okay, and if you look here, I've done it a couple ways. So I want to find the probability that x is less than 20, or probability that x is less than or equal to 20. Doesn't make any difference whether you include 20 or not. You get the same probability. So let's see. Here it is. The first one's a trace. So I just hit the trace button. That's one of those buttons up at the top, and then I type in 20 and enter, and it'll show me the point 20 for x and then the y, and that y is the cumulative probability that we're looking for. Or I can just go to the home screen and just say y1 of 20. So remember, you can get y1 as variables, right arrow to y variables, then function, and then this is the first one. If you've got the old operating system, if you've got the new operating system, you can do it the same way. But there's another shortcut for the new operating system. You can just hit alpha and then trace, and then it'll show up, and you select it from the list there. Okay, so that's one way to get it. Now, let's do a couple other things. What if you want a probability that x is greater than a? Well, it's easiest to do this from the home screen. You type 1 minus, the probability that x is greater than a is 1 minus the probability that x is less than or equal to a, so it's 1 minus CDF of a. So at the home screen, you just type 1 minus y1 of a. If you want to find the probability that x is between a and b, okay, which is the thing, it's the thing that we shaded back on the CDF curve. It looked like this one here, where it was shaded between. If we want to find the same thing using the CDF curve, then we just need to subtract two y values. So on the graph, it's seen as a vertical distance over here between two y values. So at the home screen, it's pretty simple. You just type y1 of b minus y1 of a, and that gives you the probability that x is between a and b. So you can actually compute probabilities pretty easily from either the CDF or the PDF. On the CDF, there are areas, on the PDF, there are areas between the graph and the x-axis. On the CDF, there are y values for cumulative probabilities. But one thing you can do on the CDF that you can't really do with the PDF directly is define inverse probabilities. Okay? So in this time we're solving for the x value that would be the place for which gives us the probability we want. For example, if we want to find b when the probability of x is less than b is equal to p, that's the left tail probability, p is known, then we know that the y value is p on the CDF curve. So just let y, go to your graph, let y2 be p, and that'll graph a horizontal line, and just find the intersection of that horizontal line with the CDF curve. And I think I have one of those illustrated down here somewhere. Yeah, so down here, these last two in the bottom right corner, I've got y2 is 0.6, and that graphs a horizontal line here. Then I did a calc intersect. You have to select two curves, make sure you're selecting the CDF and that horizontal line, and then you put your guess close to there and hit enter. Of course, it's going to give you a y is 0.6, and it's going to tell us x is 68 point something. Okay, so that says the probability that x is less than that 68 point something is 0.6. So that's telling us that this 68 point whatever is the 60th percentile. 60% of the data is below that. The probability that you would get something below that is 60%. Of course, if you let this y value be 0.5 instead of 0.6, now we're talking about the median. And so you do it the same way. You just put 0.5 there and get the median. So if you want to find the median, you first need to get your hands on the CDF, either know what it is or approximate it like we did before. So to find the 40th percentile, you'd put 0.4 for your horizontal line and then do a calc intersect with the CDF and that horizontal line. What if you know a right-tailed area, okay, instead of a left-tailed area? So this one should say right-tailed area. Okay. Well, remember that if you know the right-tailed area, you know the left-tailed area too, because the left-tailed area is 1 minus that. So in this case, just let y2 be 1 minus the right-tailed area, and it will be the left-tailed area, and a left-tailed probability, I should say. It's an area if we're talking about PDFs. It's actually a y value when you're talking about CDFs. Okay? And so we just graph that and do that the same as we did above. Now, just as we were able to do a CDF approximation if we knew the PDF, we can go the other way around. And I haven't actually gone over this in the other videos. So this is the first time I'm showing you this one, I think. It turns out that the PDF is something called a derivative of the CDF, and you don't have to really know what that is. All you have to know is what kind of command you can put in the calculator to make it draw the thing for you. So y3 is called the numerical derivative of y1 comma x comma x. So the old operating system would be written just like this. Actually, you can see this of these group of 5 screens right here. It's the first one up here on the left. Okay, and we've got y1 is the CDF, y2 is numerical derivative of y1 comma x, close parentheses. Boom, y2 or y3, the way I've got it here, will be your PDF then, or at least not a good approximation of it. This next one here, notice that I've got the same thing, but this is what it looks like in the new operating system. Three of these things are always x. This one down here at the bottom by the D, the last two are x's, and the one in the middle is wherever you've got your CDF, which in my case is y1. So this y3 is the same both cases. In both cases, to get this, you push math 8. So math 8 to get this thing here, and there it is. And then you can graph that, and that'll be the PDF if you need that. Now here it is on the same scale. It's kind of small, so what I did next is I turned off the CDF and just graphed the PDF, but I zoomed in quite a bit. So now I'm only graphing from a top of 0.02 and a bottom of negative 0.002, and then here we get something right here. And so we get a nice little curve like that. Okay, and we can use that. Once we have that, we can compute the mean and the variance and the standard deviation of this guy, just like we did before. Remember in the last case over here, remember how we did the mean? Let's see, here, let me show you the actual picture of it. Right here's where we computed the mean was function integrate x times y1 and so forth. Well, what are we going to do this time? Instead of y1, it's going to be wherever the PDF is, which is y3 this time. And this is always x. And then here we're going to have to pick something that's going to be way out there. And maybe for this one, I'm not sure what would work, but let's say maybe negative 1,000 to 1,000 might be sufficient. Okay? And similarly, we could do this kind of thing here. Store the mean is m, and then we use exactly this formula here, except again negative 1,000 to 1,000, and that'll compute the variance, square root to get the standard deviation. So you can see from these examples, it's sort of laid out step by step all the different things that you can do with the calculator to get the things that we need, okay, for probability distributions. Okay, and there's really nothing else to it. Now, what's going to happen a little bit later on down the line is there are some types of functions that are important to us that we're going to use a lot, like normal, a t, a chi-square, an f, some of these distributions are very important to us, and so they're built in the calculator. And the calculator may have a PDF built in, it may have a CDF built in, might have both, but we see here, as long as it's got either one of those built in, we can use it to get everything we need. If it's got both built in, even better. In a couple of cases, it even has a built-in inverse function already, so we don't have to draw the horizontal line and calculate the intersection. That's an even nicer shortcut. But even if it doesn't have that, as long as we can get our hands on a as long as we get our hands on a CDF, cumulative density function, then we can do inverse probabilities. As long as we can get our hands on a PDF, then we can calculate means and variances. And we can calculate probabilities from either one.